Добре, на какъв език водим тук? На JavaScript викат, добре. I assume I will need to speak in English, so I will resume in English then. So my name is Martin. I'm a software architect, one of the senior software architects at DraftKings. And we have extensive experience with variety of technologies, one of them being JavaScript, obviously. And we have also a lot of experience of transporting information around the world. And today I'm going to share with you some of the lessons that I've learned personally when dealing with WebSockets. I usually steal stuff from the office to bring to conferences to throw at people. So I have some ducks. If you want a duck, you should ask a question. And if it's a good one, I will answer it, and you will get a duck. There is also a mathematical joke hidden somewhere around the slides, and I promise a special reward if somebody notices it. Okay, I have a camera, so let's make the camera guy work. I will move around. This story starts at Christmas. And back then, I was team lead. I had people that I managed, and I managed to let them on holidays somehow at the same time, so I was covering for them. And I had some time to play with WebSockets, because everybody else was on holiday and there was nothing being deployed. So this is how our story of using WebSockets actually began. All right? I will have a disclaimer here. Today I will share with you a lot of information about how to use WebSockets properly, but I want you to know that the only right answer is it depends. So today I will say, and I will tell you how you could do load balancing. I will not tell you if you need to do load balancing, okay? Is that clear? So if you need to do load balancing, this is one way to do it. Is there a lot of echo, or this is something that... Can we do something about the echo? Kopče. They say it's okay. All right, so with that said, how can an answer change by it depends, right? So if you're designing an internal system, the rules might be different. If you're designing SDK for some other people, the answer could be different. If you own both the client and the server, the answer will be different, right? So there are many things that could affect this. All right, so quick overview of the agenda. I'm going to share with you some things about the lifecycle of a socket, some of the use cases where sockets are beneficial, some of the benefits of WebSockets, and then I'm going to go into the challenges, and this is where the meat of this talk is going to be. So what is a WebSocket? A WebSocket is an API. It's basically a messaging protocol, and what that means we're going to discuss slightly later. And WebSockets, not to be mistaken for Unix-style sockets, are a browser API, which is actually widely supported in many different places. So how do we know that? Well, we can check. So WebSockets are making developers happy since 2010. Some developers maybe are crying. How does a typical HTTP connection look like? So in the typical HTTP connection lifecycle, we have DNS lookup, connect, send, wait. After the resource is downloaded, then we close the connection, and that's it. With Socket, it's slightly different. We're going to explore how the lifecycle of the socket looks through a property called ready state. So WebSockets, they have a property which is called ready state. How do you get a WebSocket? Like this. By the way, that's all the code that I'm going to show today. I couldn't come here without any kind of JavaScript, so I had to put something. But we're mostly interested in the ready state, and this is where the interesting part starts. So, client and server communicate. Usually how this happens is that we're sending as a regular HTTP connection from the web browser to our client an HTTP upgrade request. And what happens is that the server agrees that it can handle WebSockets and gives us an upgrade of HTTP code 101, if I remember correctly. Yes. So we're switching protocols. Now we're talking WebSockets. That's all. During the ready state 1, we're already in open state, and we can send frames or messages, and the server can respond. And we can send more messages, and the server can respond more. And at some point in time, we are going to say, okay, we don't care about this communication anymore. We're going to say, finish it, cut it off. The server will agree, and we will have terminated the connection, and now the ready state is going to be 3. So this is basically how the WebSockets work. It's a bidirectional pipe where we can send and receive messages. Why is that interesting? Well, this is interesting because we can do a lot of interesting real-time things with bidirectional communication. So we can have sports feeds. We can stream data that's happening live on the field to customers. Trading systems work in similar way. So if you've seen any trading system that goes up and down quickly, that's not polling, that's sockets usually. We can have telemetry from devices, we can have any number of other use cases, multiplayer games, collaborative editing of files, and so on and so on and so on. Data visualization, remote control of devices, conferencing, even development tools. The common thing here is that we want to reduce the communication delay here as much as possible. And some of the benefits of WebSockets actually are intended for reducing the amount of communication delay that we have. So WebSockets, in general, are wire traffic efficient. What this means is that they incur less traffic than HTTP in general. So why they incur less traffic, we're going to talk about this a bit later. You don't have to deal with cores. Anybody ever had issues with cores? Okay, I'm in the right place. No cores for WebSockets. They have very simple API. The API is basically new WebSocket, on message, do this, send message. It's like it has 2 methods, that's all. And they're bidirectional, which means that we open a channel between us, and only us two can communicate on this channel. Obviously, real-time communication. They're available in web workers. Anybody has used them? Web workers? Like 6, 7 guys, nice. And they're also available on mobile devices, on .NET, on Kotlin, on Swift, on whatever you can imagine. So that's the good parts. Now let's talk about the challenges. Now before I continue, has anybody of you ever used WebSockets? Oh, nice. How many of you did their own implementation of WebSockets? Okay, much less. The other people, what did you use? Shout it out. SignalR. That's a sad story. Most of the challenges that I'm going to describe are also somewhat connected to SignalR as well. Okay, what else besides SignalR? Can you shout it out? MQTT over WebSocket, nice. That's a nice use case. Anything else? Socket.io, cool. So for the few brave people that used raw WebSockets, I'm sure that this is what convinced you to start. And this is what you got eventually. The server that was intended to host the socket eventually started shipping data from other things from your internal system because you don't want to open too many sockets to the end client. But you're also passing through some kind of gateway and load balancer until you get there, right? So it's not so simple. And by the way, on this picture, you don't see CDNs, you don't see firewalls, you don't see how the backend services are scaled and so on. So this is actually a very, very simplified view of what you get eventually with WebSockets. So some of the challenges, and actually those are the top picks. At the end, there will be an honorable mentions slide where I will have some more. But some of them have to deal with state management, how long-lived connections are generally treated over a network. We have application security, we have network security, we have application performance monitoring, we have backpressure. Anybody, most of you raised their hands about WebSockets. How many of you had to deal with backpressure? One guy, two guys? Wow. It's very, very tricky to debug. What else? Protocol efficiency. Oh my, there's so many things here. So let's start with state management. That's the simplest one. If you open a socket, you have state. That's it. Now, how this state is going to complicate your life is very, very tricky. So how many of you had to ever use sticky sessions? Okay, a few of you. Nice. So this is a challenge that very few people are experiencing. So what's a sticky session? So sticky session is one-to-one relationship between the client and some kind of backend service. Okay, let's take it like this. If you break the sticky session, user might get locked out, or the transaction could be canceled because the request went to another server. And this is actually one of the interesting challenges with SignalR. If you have properly load-balanced system, you could get to a situation where the handshake of SignalR is going to one server, but the actual request is hitting another server. So SignalR is a protocol of itself, and it has a handshake where client says, I know WebSockets and HTTP, and server says, I also know WebSockets and HTTP, and then client tries to open WebSocket connection, but it hits another server because the load balancer rerouted it, and the other server does not recognize the handshake, so rejects the connection. So what you can do with sticky sessions, this one-to-one mapping between client and server, you should try to break it. And if you really, really need some kind of state on the back end, you can still do it, but you need to externalize it. Now, what's the good thing about externalizing state between all the servers that are managing your WebSocket connections? Shout for a duck, come on. Does that look like something nice to do in your system? It's another bottleneck. It's another single point of failure. It's another thing that you need to scale, shard, yada, 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 yada. So, how to load balance long-lived connections? Sockets are long-lived connections, and they bring interesting challenges in load balancing. For example, if you want to load balance them, you need to do something very, very special that I will show in a second. But you're also in a situation where you can overload the backend. Because this is a long-lived connection, you cannot randomly cut it, right? Obviously, you're using socket because you want a long-lived connection. You don't want it to randomly disappear. So you need to handle disconnects in a variety of cases. And if you need to handle a disconnect, you need to, the client need to be able to reconcile the state, right? Very, very unfortunate. And deployments and rolling deployments become increasingly complicated when you need to load balance long-lived connections. How does that look like? Imagine that we have this running system. It's perfectly load balanced as it should be, like all things in life. And one of the servers sporadically dies, or it gets redeployed and restarted. So suddenly some of the traffic was sent to one of the other servers. But now there is no reason for us to load balance it back to the first one after it comes back sometime later. But eventually we can overload, I skipped a frame here, eventually we can start overloading other servers that were redistributing traffic, and they can start dying. And after they get either redeployed or restarted, we're in a situation where there is no reason to move connections to them, right? You don't know when to cut a live connection with the user. So at that point, those servers get overloaded. So you move them to the upper two ones. And you get into this constant situation of switching them because there is no mechanism to actually move an actual connection between two servers, right? So that's a tricky problem. So how do we get back to this kind of situation? So this is the first thing that we're going to mention today, which is related to network security and application security, both at the same time, kind of. Gateway cutoff. In the initial image, there is a gateway, right? This gateway must decide when to cut off the connection. And this must be handled by the client. The client must know that the gateway at any point in time could decide to redistribute what through the system and cut the connection. And this could be scheduled, maybe every 5 minutes or every 10 minutes, whatever works for you, obviously. But the interesting thing here is that if you don't have this, there is no way to cut the connections besides killing a server. And once you kill a server, all the connections will go to the other one. So even if you decide to kill all servers, the first one that gets live will get all the traffic, and it will die. And this will happen over and over and over again. So a couple of things that you could do on the client. So if you need to manage WebSockets on the client, you can do a couple of things. You can randomize connection lifetime. So the client can say, okay, my connection for this session is going to be 7 minutes. The other client can say it's going to be 10, or it's going to be 5, and so on. Another thing that you can do is you could schedule connection refresh. It's kind of the same like randomized connection lifetime, but not exactly the same. Or you can scale also on the back end based on number of connections supported. So you will never let the server get exhausted their number of possible connections. Why is that possible to happen? Because of connection fan out. Because in the initial picture, you see that one client socket is actually doing multiple connections to the backend. So eventually you can exhaust the connection pool of your server. Backpressure. To the only 2 other guys here that experienced this, how did you solve it? How? Ah, with throttling. Okay, you get a duck. That was close. For all the people that didn't see, that was a hit. So what is backpressure for those that haven't experienced it? Backpressure is when we are overwhelming somebody with requests that they cannot handle. Now, usually when this happens in ideal situation, you're going to get as many messages as you can handle, right, from both sides. But what we usually do, we handle this for the backend, but we don't handle it for the front end. We very rarely think about the device that's actually going to need to handle the amount of messages that we're sending. So what happens when the device cannot handle 10 messages per second? It can handle 5. So we start getting congestion. And this congestion actually starts spreading to the backend, because why we want to push many messages? Because our backend is trying to push many messages. And this server is actually proxy. So backpressure starts pushing back on our entire infrastructure eventually. And we start getting very weird things that are very, very hard to debug. For example, if you exhaust the TCP stack, the TCP send stack, how do you debug this? You're never going to get an error in the application. The server is not going to get an error. So you go debugging operating system logs eventually. So this is why backpressure is so nasty to handle. And also another point of backpressure could be the internet itself. So we can have multiple reasons for backpressure. We can exhaust the underlying network protocol, the TCP/IP protocol. We could exhaust the receive or send queues of the TCP stack, or the device resources could be exhausted by the need to handle so many messages. So I don't have any more CPU. That's all you get. Like I can process 5. If you send 10, I die. That's it. Or another thing, the medium that we use to send them. So mobile networks are unreliable, right? So retransmission is something very nice. TCP handles, guarantees delivery. So what it means that if you have some kind of packet lost around the network, it will try to retransmit it. And until that packet gets to you, you cannot send any more packets, because they're piping behind it, right? You cannot process the data before you get the data. So when you get a message lost, you eventually wait. And then we start filling the stacks again, the send queue and the receive queue. Now, a couple of things we can do to handle them. A colleague here said throttling, which is nice, not always an option though. So we can do compression. And compression could be not only gzip, right? You could think on how to compress and reduce the data that you're sending. That's one thing. You could try to control the rate of messaging, which is throttling, or you can do compaction. Compaction of data is something very interesting. It is obviously not applicable everywhere. But think about it like this. We are dealing with sports, right? So if you're sending events related to sports, you could actually say, fine, but it looks like a message to be sent takes X amount of time. And for that X amount of time, we have X number of changes. So maybe I care only about one of those changes, and I don't need to send all the rest. The client, so if you're generating one message every 20 milliseconds, and the client can get one message every 200 milliseconds, it doesn't make sense to send them every 20, right? So you could skip some updates, and you can decide how to push proactively only the relevant data. Another way to do compaction is do sparse contracts, send only what changed. So send only the difference. This is also another way to do compaction. Buffering, throttling, at the end of the day, dropping. Just, that's it, drop the messages. You cannot send them anyway. I skipped showing them. Protocol efficiency. So I said, actually in the beginning that WebSockets are a protocol. And what you see here is a frame. And what is a frame? The frame is the message that you can send over the WebSocket. And since this is an ugly picture taken from the RFC, I'm going to change it to this. The important thing here is that these messages can be very, very big. Let's rename them to something nice. So those messages can be really, really big, like 4 gigabytes, something like that, right? Now, how do those messages get transferred over the wire? They don't go as one message, are they? They go as TCP packets. Yay. Now, if you have messaging protocol built on top of a streaming protocol, now you have a problem. Because the message can be only understood by the system when it's transferred completely. And the stream doesn't have, TCP doesn't care about messages. TCP streams any kind of chunks that you try to send. And you are responsible for deserializing them. So what happens is that this nice frame that you're trying to send, this big JSON, is actually going to be split to many, many, many small packets. And they're going to go through the wire. So what will happen then is that if you decide to send big chunks of data over WebSockets, you can saturate the link. So, has anybody experienced this problem? The MQTT guys? No? Very small amount of this problem. So eventually saturating the link means that the client will not be able to send data back. So it will not be able to tell you more information, but also if you're trying to send packets from multiple places, you will not be able to because there is no multiplexing in TCP. It just sends whatever you put in the pipe. It doesn't care. But if it skips a package, so if you don't send acknowledgement for a package, it will try to retransmit it again, which means you will not be able to parse the message until you get all the packets. And you get into this constant situation of not being able to parse your data, which is very, very annoying. Now, obviously, the fact that the protocol, WebSockets protocol supports sending 4 gigabytes messages doesn't mean you should, okay? So the fact that this is running over TCP IP, which is a very, very leaky abstraction, you need to care about this and you need to craft your data in a way that you will be able to actually reliably send it. So can you split those 4 gigabytes into small messages yourself, for example? Or you need one huge chunk? These kind of things. By the way, sending a 4 gigabyte message means that you need at least twice the amount of memory to parse it, to deserialize it into some data structure. So obviously JSON is very, very convenient. This is why I wrote juicy JSON earlier. Security. Any problems with security with people who used WebSockets? Just ignore it. If you get it. You sleep well, my friend. So in what cases we can ignore security? It's a good thing to say. In an entirely internal system where you control the entry points, this is where you can ignore security between services. Generally, if it's user-facing, like we most commonly do with web browsers, you cannot, sadly. So there's three things that I'm going to touch today. Obviously, the topic is much deeper. I'm going to mention authentication, authorization, and user input, because those are more interesting with sockets. So let's take the first system that I showed. We have the following situation. We somehow need to allow those clients to get to those servers. So what do we do? Well, we can allow the gateway to control this. And let's say we have some kind of services related to account control and login. So we can issue a token for the client. And on the opening handshake of the socket, we can use the token. And then the gateway is going to strip the token because we don't want our system to understand anything about those tokens. And we're going to write headers like user ID, authorization ID, whatever else ID that we care about. And this is data with which our servers can work. Now, it's important to understand that those servers should not understand anything about security. And I'll explain why. Because this doesn't mean that I don't want you to have security. Those servers should not understand anything about security. If you're streaming data, you're generally not doing transactions, right? We're talking about bidirectional communication, chat application. So what kind of security will be needed here? After the connection is established and the gateway allowed it to get established, you should stream data. And then the question is, what do we do if the token expires? The gateway cuts off the connection. That's it. For the server, the connection is just closed. The client will need to reopen it, and if they need to re-authenticate, they will do it, and that's fine. But the backend should be kept clean. Now, we get to the zero trust type of approach to security. I'm not saying that you should do your wallet, your deposit, or your withdrawals like this. I'm saying that you should stream data in this way. If you need to do wallet transaction, some kind of special kind of transaction, it's okay to have MFA, to have zero trust approach and architecture, and to do re-authentication at that point as well. So you could have somewhere here another type of service that requires special type of authentication, and that's fine. But generally, most of your system will never require this kind of security. User input. Now with sockets, WAF is Web Application Firewall. So with WebSockets, if you remember from the first slides, they get opened through a normal HTTP connection or HTTPS connection. The problem is that the Web Application Firewall recognizes this and it's fine with it. And once you establish the connection, the Web Application Firewall does not see anything that's moving on the connection. So what happens is that your server needs to have protection against user input, malicious user input. So after I establish the socket connection, I can actually try to DDoS you through the socket connection. And no CDN is going to stop me, no web firewall is going to stop me. So actually your server needs to handle this kind of protection there. You cannot trust Elastic Load Balancer, you cannot trust Azure, whatever they have, you cannot trust Nginx, yada, yada, yada. No, your server needs to have the protection. Some of the things that you could do, establish timeouts, forced timeouts for handling messages, for example. If you're getting high rate of messages, you can apply rate limiters. You could forcibly close the connection. And something actually really funny, you could return garbage data. If you get too many messages, you could actually return garbage data, which is very, very funny to observe. So this kind of protection, very important. It must happen on the server. Application performance monitoring. A lot of people raised hands here. How do you measure the performance of your WebSockets? We don't. Brave people. Somebody that does? No. Nobody measures performance? One person in the room? I'm not sure if I can throw a duck so far back. but I will spare one for you. So over there, they measure the page rendering and the number of socket messages, correct? How do you measure the number of WebSocket messages? They do testing. So no proactive monitoring. Okay. Custom what? Custom metric in AWS. So there is amazing tooling for HTTP. Like you could just get New Relic and click start, and you get full picture of all the requests that are running through the system. With WebSockets, you get nothing. You need to sort it out for yourself. If you want to measure the WebSockets, you need to do this on your own. And how many messages did you receive? How many messages did you send? Did you receive all the messages that you had to receive? Did you miss anything? Was it important? Should I have missed it at all? All those questions, obviously, they depend on the type of software, but you need to find a way to answer them, and you need to find a way to monitor them. Which means that the developers that are actually implementing this system need to implement additional piece of code, which is reporting this information. So to this GUID, I send 700 messages, and the GUID reports that received 600. So I lost 100 messages. What do we do now? Should we make sure that those messages are sent? Did we get backpressure in the system and the messages got dropped? How did they get lost? Like, how did I miss 100 updates? That's a question that you should be able to answer if you're using WebSockets and if you need to do streaming. Another thing about debugging. How many of you use a Chromium-based browser for work? Come on, don't be shy. Wake up, raise the hands. I know that all of you are using something Chrome-based. So, a note, if you have to debug WebSockets, you cannot use the browser tools to do that, for the simple reason that the throttling that you get in the web browser is actually a fetch polyfill. So it does not affect the WebSocket constructor at all. The only way for you to check the behavior of the socket when connection drops is to actually pull out the cable. Yeah, pull out. So the only way to simulate disconnect is to actually cut the network or pull the cable out. A couple of honorable mentions. I kind of mentioned head of line blocking. This is what happens if you transfer a big chunk, a big message into many TCP packets and one gets lost. Until that packet is retransmitted and reordered by the TCP stack, you cannot parse the message. But they stay in the receive buffer of the TCP stack, which could eventually get overflown because you're continuing to send messages, and I lost only one packet. No caching. If you want caching, the client needs to do the caching. There is no CDN, no distributed network that can help you cache any kind of messages for WebSockets. Connection fan out. So it's very tempting and nice and beautiful to have BFFs, backends for frontends that simplify the work of the client, and you have one connection with the client and everything is peachy and nice, and this one connection to the client leads to 300 connections to your own backend. So this simplification actually comes at a cost, and you need to be aware of this cost, and you need to also manage that cost. Because eventually, if you design the system in such a way, you're going to be exhausting the connections limit, and you will have CPUs that are not very busy on your machines, but you will need to spawn many instances because of the connections limit. And this becomes very interesting when you have millions of users. Because it doesn't sound too interesting if you have like 300 users and they create a few thousand connections. So generally the connection pool is about 50,000 connections, right? So it doesn't sound too impressive. Now multiply it by several millions and it becomes very interesting. Sniffing. This is a security concern that you could have. It's the same as with HTTP. If you're using HTTP, not HTTPS, or if you're using VS, not VSS, secure WebSocket, you will be vulnerable to the same things. Because WebSockets, generally they transfer text. They don't transfer binary, okay? The last one, I have few ducks. Can anybody tell me what is the last one? Come on, Google it. Okay, cross-site, WebSocket, hijacking. Cross-site WebSocket hijacking is the same as CRF, cross-site request forgery. This could happen if you're transferring important data. You need to make sure that you're not only using VSS, but you also have other mechanisms of protecting the data. Because the same vulnerabilities that HTTP has, WebSockets also have. Another question, is it worth it to use WebSockets if you can use pool? Who said yes? You get a duck. Can you raise the hand? Let me try to. Direct hit. So, what else are you going to use? Okay? If you need real-time communication, bi-directional communication, what else are going to use? What, pigeons? You don't have a choice. What? I will talk about that in a second. So, that's it. This is what you can use. So yeah, when it's worth it, it's worth it. Now, what are the alternatives? Generally, there are three alternatives that can help you with this. You could have the standard polling, not a very good practice nowadays. You could have SSE, server sent events, or you could use WebRTC, and I promise you, I always forget what kind of streaming is RTC. Now, obviously, those three are not one-to-one mapping with the features that you need. Let's start with polling. With polling, it's great for big files, big amounts of data. You should definitely poll. Don't flush them through the socket. This is fine. Works everywhere. Very cool. Now, with polling, you have something that's called headers overhead. Polling is good for big files, but why it's not good for small files? For small amounts of data, the headers that you're actually sending on each HTTP request are more than the data. So you have around 10K of bullshit there that you don't need. So if you're sending 1 kilobyte of data, polling is not very good. You should maybe stream it with SSC, but don't poll. The other thing is maximum latency. So with maximum latency, what does it mean? When you open a poll request, the server will hang the request as much as it can before the browser cuts it off or any proxy along the way cuts it off. But let's say it will hold the request as much as it can, open. And if it doesn't have anything for 20 seconds, it will close it. And then you will need to reopen it again. And you already missed an update because the opening itself also takes hundreds of milliseconds. And timeouts, which I mentioned kind of. Any proxy along the way could have a timeout that you did not configure. So this is why generally we don't wait for default timeouts. We have our own when we use sockets. The other alternative is server sent events, and they're very, very cool. I love them and I hate them at the same time. They are the forgotten protocol of the web. So they showed a lot of promise when they came out a few years ago. Now nobody uses them. With SSE, you have a read-only stream of data from one point to the other, which is very nice. It is a protocol. And why is that good? Because with SSE, it tells you you need to implement IDs of messages, and it handles reconnect automatically, and it sends to the server the last ID of message that it receives, and it expects the server to stream the delta. So this is why it's a very, very interesting protocol. Very nice. If you don't need to send outdated messages, it's not your protocol. But the nice thing is at least it reconnects automatically. You don't need to handle reconnects. No header overhead. You open once and that's it. Now, it's a protocol, it's both a pro and a con, because if you don't implement the protocol properly, it's not SSC, it's something else. And people who expect to get SSC will not get SSC, and they will need to handle reconciliation of state and so on, because, for example, you're not sending delta. Another thing, it's fixed direction of the flow. So once you open the stream, the entity that we call the server is only able to push data. That's it. You cannot change the subscription. You need to cut it off and open a new subscription. So why is that a problem? Well, because we get back to the same place. We open a new HTTP request and so on. Besides that, SSC has all the challenges with WebSockets that I mentioned. So it's kind of lesser WebSockets that can talk only on in one direction. Another problem is that it does not support any headers. So how do we do authentication? If we don't have any headers, no authorization header, no headers. How could we do authentication? Query parameters. Don't you love a JWT token attached as a query parameter? It looks amazing. So this kind of kills the deal, because even if I'm happy with what I'm getting here and I can solve the problems with the WebSockets and everything, I'm still in a very, very stupid situation where I cannot do proper authentication with this. I need to send stuff as query parameters. So generally same challenges as WebSockets. The alternative WebRTC, and this is really, really nice. This is real-time communication, but it could work over UDP instead of TCP. And why is that interesting? This is interesting because if you want to stream video, like live video, and you skip a frame, well, you technically don't care about the frame that you skipped 2 seconds ago. You want the new frames. But with TCP, you're going to try to do your best to retransmit the frame that missed, because TCP promises it will retransmit it until you get it. And if you lose a couple of them, it will do its best to transmit all the ones that you lost. And usually, when you get packet loss, when the network is congested, and trying to transmit the package that you already lost is what? Congesting the network further, which is insane. So WebRTC allows you to choose if you want guaranteed delivery or unguaranteed delivery. So you could choose UDP or TCP. This is nice because you could prioritize them. So if you somehow hit a client that filters all the UDP traffic, like a defaultly configured firewall, for example, you will still be able to use TCP for this client. Polyfills, why would we need polyfills for SSC? Well, because SSC does not support headers and people want to do proper authentication, so they built polyfill for SSC over this. So this is actually very, very powerful. And you could do bidirectional or unidirectional communication. However, you could also do this kind of communication from the client to the server. With SSC, we are getting always server to client. But with this, we could open a stream writer, and we could send over this connection messages from the client. So we could have either client to server, server to client, or both. And we could choose if we want reliable delivery or unreliable delivery. So it's very, very powerful and very, very nice. It's good for streaming, video, audio, live conferences, things like this. And now I have a question and 3 ducks. One is promised, so I have 2 ducks to give. What is this? So the only reason I can tell you is because I have it written in front of me. No session. Datagram transport layer security. SCTP is a stream control transmission protocol. SRTP is secure real-time transport protocol. ICE is very nice. It stands for Interactive Connectivity Establishment. STUN. session traversal utilities for NAT, NAT. And what is turn? Traversal using relay NAT, NAT. So the learning curve of this is not as with WebSockets. It's very powerful, you could do everything. And you know how you use it? You actually do fetch. You know JavaScript fetch, everybody knows it, right? You do fetch to a URL with post, put, delete, whatever kind of request. You could open this kind of connection and you attach a reader and a writer to this connection and it keeps it alive. But then what you do is you need to have your own protocol built on top of it. And then you need to invent a protocol that's suitable for your application. Why? Because JSON can no longer be deserialized. If you're using UDP and you lose a message, there is no way for you to deserialize it anymore. So now you need to have your own protocol that's optimized for your use case. And it's a protocol that you will be able to serialize chunks of data with data missing, which means that the data that you're sending needs to take care of its size. And TCP is very, very nice and everything is super cool until you need to understand how much data can a packet hold. So what's the minimum size of a TCP packet? Of a network layer packet? What's the minimum size? I have a duck for this. How much?
500.
No. How many? No. No. It has 10 frames of 1,400 bytes. That's the smallest TCP packet. But the UDP packet, how much is it? Come on, Google it. How many? 8? I don't hear. 8. Did you Google it? Good. You get a duck. I cannot throw them. They're very light. I cannot throw it so far. So, very powerful, steep learning curve. And also you need to learn how the underlying network works. So if you're using UDP as main transport and TCP as backup transport, you need to take care of both limitations. Now, key takeaways. Do you really need bidirectional communication? If the answer is yes, you need to do all of these things. If you can find a way not to have bidirectional communication, well, just put an Nginx in front of it and you'll be happy. WebSockets are super useful, but they come with a price. And the tutorials that you can see around the web, they very rarely speak about this. And most people who know this had to actually deal with WebSockets on production and had to struggle to stabilize a system with WebSockets. By the way, you cannot just randomly decide that you want to use WebSockets. So, no, you can, but you cannot make them work. Your backend system needs to be designed in a way that can support streaming to a client. And it can support security over streaming to a client and things like that. To be efficient, by the way, WebSockets support text, so JSON is very, very nice, but also JSON is very, very expensive. So if you want to be efficient, you need to design your own protocol. Just for an example, protobuf takes half the size of JSON, and it's actually 10 times faster to deserialize. Why? What? It's binary, but why it's faster to deserialize than something that's natively supported in the browser? Please shout up. You know what you're sending. I'm sending you a number. You know what happens when the browser receives JSON? It's a string. Is it a date? Is it a number? Is it an array? Is it an object of any other things? So this huge complex deserialization kicks in, and it's slow by design. There is no way to make it work because there are no strict types. So protobuf, for example, and by the way, message pack as well, I'm not like fan of one or either. Protocols that tell you what they bring, they are much, much faster to deserialize, and they take much less memory on the client device. Some advice from myself. What we did, we actually abstracted the transport protocol in a package, and we allow our developers to import something with nice interface. Is it polling? Is it socket? Is it SC? Behind it, they don't know. Obviously, people who maintain the package know. But what developers are getting is, give me that, and give me listener for data. So if I change eventually the protocol from something, it's a transparent change for them. So what happens is I just deploy a new runtime package, a package that's resolved runtime, and that's it. The application switches protocol. Not exactly. Somebody said just like SignalR. The problem with SignalR is that with their handshake and their requirements for backend, they're actually, they cannot handle huge WADs, huge system WADs, and they're not very scalable. It's a nice start for something. Okay, I don't know how to do sockets. There is some kind of interface here. Let's do it quickly. Nugget install, npm install. But then when you start actually needing to scale and have a performance system, SignalR is not a good answer. It's for small projects. So that's all. I have some time for questions, and I have 2 ducks. No, 1 duck. I have 1 there and 1 there. If you have any questions, that's the time. If not, yes, shoot.
Seems like we invented the wheel with WebSockets. To me, is there something previous, like solution, someone who's good with WebSockets can use to solve most common problems? Because
wait.
Problems are common.
Just a sec. So I will repeat this one, but generally we could use a mic, but try to keep questions to 1 sentence, because when you try to ask 5 questions, it's very hard for me. So let's play it.
Can you hear me? Okay. Yeah. Seems like you reinvented the wheel with WebSockets. Is there something pre-built which someone who don't have any experience with WebSockets can grab and start experimenting?
So something with what I started is that it's very easy to start with WebSockets. It's very hard to do application and network security with WebSockets. And since each application is more or less different and requires different messaging pattern, different kind of protocol, different kind of type of data even is moving to it, there is no like super generic out-of-the-box solution that you can use. Like even if you take SignalR or Socket.io or whatever, well, you still need to do security, you still need to do authentication, you still need to do authorization, you still need to take care of user input, of rate limiting, you still need to take care of tokens getting expired, things like this. So there is no system that can give you this out of the box. So you need to build it your own. It's not, the problem is not with WebSocket itself. So let me show you this again.
Because my understanding about WebSockets was exactly the first white you show, and then the second with all the complexity totally changed my mind. And I was thinking how it's possible to not have a clear way to monitor the loading and so on if it's so powerful.
Well, you can. You need to implement it on your own, because there is no way to standardize something that is so fundamental. Like this is the abstraction, right? So this is the abstraction. Now you need to decide what to do with this abstraction. And actually, using WebSockets is as easy as this. And you can successfully use WebSockets like this, but somebody will steal your data, or somebody will crash your system, or you will pay huge bills for Amazon Cloud because it's continuing to auto-scale with the world. So if you want to have a reliable system, you need to do these things. That's it. And like, there is no system design out of the box. Like, I want a socket system and boom, get this. Like those services, these are random things that I thought for the conference. But in our real backend, we have systems on the backend that are communicating with SSE. We have things that are communicating with MQTT as well. We have Kafka streams. We have many, many things that are eventually getting to a BFF that ships it to the end user. Do you need this? Or maybe not. Maybe this server for you can also handle authentication because you have 5 users a month. I don't know. You get my point. The solution must fit the problem. It's not like get a solution and then find the problem for it. I have 5 more minutes. Okay, I will take one more question. You get that.
Hi, Martin. Great talk. Can you share some things we can look for to detect backpressure?
Didn't catch that quite well.
Can you share some things we should watch out for so that we can detect backpressure?
Now that's a good question. How to detect backpressure? Well, if you look for backpressure, you will eventually be able to detect it. Now, very thing that I missed. Actually, WebSocket API does not have control flow mechanism. So you will not be able to detect it there, okay? But if you start getting congestion here, you could have a mechanism to understand that, okay, maybe we are not sending all the messages at the rate that we expect. You could have a monitor, so every time the client receives a message, it could report what it received. Now, is that going to overwhelm your backend? Probably yes, so you need to do sampling. Now, what kind of sampling are you going to employ here? Only you can tell. 1% of the users? 10% of the users? I don't know. Critical system? All users must report on all messages? I don't know. It depends on the type of system. But if you want to stream huge amount of data and you don't really care about complete delivery, like TCP guaranteed delivery, maybe use WebRTC and the UDP protocol. Maybe it's fine to drop some messages. So with backpressure, you get backpressure because TCP here will do its best to deliver the messages, right? And this is how you're going to exhaust the stacks. But this will not happen if you're sending 5 messages like that. This is a very, very simple example. In some of the early systems that we designed and developed, we wanted almost real-time change of odds. You know what happened? We killed any device that connects to this. The rate at which our backend processes and generate change, there is no client device that can handle. So eventually this is what's going to happen with your system. If you need to stream such a huge amount of data, you need to handle it. Now, since I am overstaying my welcome here, we can talk more on the outside. Thank you for your attention. Thank you for being here today.